Welcome. We are
Yeah, she messed it up. Yeah, guys, welcome once more to our YouTube channel.
So today's video would really revolve around Kepler's second law of planetary motion, which basically says that the reduced line joining the planet to the sun sweeps down equal areas in equal time intervals. We'll also be looking at the concept of the torque that is generated on each planet as a result of this gravitational force the sun exerts on it. We'll also be looking at the law of conservation of angular momentum, because of course if there's a torque at on a particular planet, then of course we can go ahead and talk about the aspect of angular momentum on that planet. We would also look at some weirdly eccentric concepts of approximations, mathematical approximations, in order to be able to solve some really fluid here. This was a problem in the KC National STEM Competition 2023, particularly in the physics advanced level entry. I hope you enjoy it and let us hop in. So yeah, this is the full question. You can just go ahead and pause the video and read the question and even attempt solving it. You can share your findings down in the comment section even before checking out the complete video. All right, let's. Okay, so Roman 1 says the torque on Pluto at R reduced to Fg. For calculate torque, you just basically what you want to recognize the forces acting on the particle. In this case, our Fg, the gravitational force the sun exerts on the planet, and then you cross that position vector, which in this case R vec. But it really does not matter the orientation of this position vector. It really can point towards the sun or it can point away from the sun. It really does not matter. But again, I'm using away from the sun simply because I don't want um, I want to avoid ambiguity cases with it having to align with this gravitational force. All right. So that's why I'm putting it outside. But some other textbooks and maybe some other references, they can actually point this guy towards the sun. That's fine. Um, so the torque is again, like I said, they cross those two, the force acting on it and the position vector. Again, the cross product is what? Magnitude of the two vectors multiplied by the sine of the angle between them. But what's the angle between them? Look at the two of them are anti-parallel, so the angle between them is 180 degrees. So sine 180 is basically zero. So the torque on the planet is 0 Newton meter. Okay, so we can go ahead and talk about Roman 2, which says given that Pluto takes delta t to move from r prime to r prime prime, and that's the distance r prime prime is a straight line. Express r prime prime in terms of v vec and delta t. Okay, so watch this, people. This planet moves along a straight line from r prime to r prime prime, because again we're assuming that this distance is so small that r prime prime approximates to a straight line. Look at how good this approximation is. Look at this tangent that I've drawn along from r prime. You see that it maintains a straight line all the way to r prime prime, right? So the distance r prime prime seems to align on this straight line, which then again tells you that that's the straight line the planet moves on from r prime to r prime prime. That's fine, right? Now, but also notice that it moves with this particular velocity v vec, because again, there's no acceleration along this tangential direction. So there's the tangential component of the acceleration is zero. So that means that the velocity of the particle along this straight line is a constant. So that means that what we have uh, s equals ut plus half at squared, and our a is basically zero. So we simply have s equals ut, which and our s now is the distance from r prime to r prime prime, right? And our u there is basically velocity v vec, and then our t there is basically the delta t, which it takes to move from r prime to r prime prime, right? That's it, right? So our s is v vec dot delta t. That's our good. Now, remember we're not using plus half at squared because again the acceleration on this planet is actually pointed towards the sun. That's the centripetal acceleration, so there's no tangential acceleration. And so you realize that well our r prime prime is basically v bar dot delta t. We can go ahead and look at Roman 3, which says that given that r vec is approximately the same as Pluto moves from r prime to r prime prime, what is the expression of dA in terms of r? Okay, so Roman 3, our dA here, look at from r prime to r prime prime, it's a straight line. So this approximates to a triangle right here. So if it approximates to a triangle, what's the area of a triangle? It's half base times height. What's our base here? Our base here is basically r prime prime, and that base is what? V delta t. So we now have the fact that we have v delta t here. So like again, like I said, base here is just r prime, which is therefore just v delta t, which is our v delta t here. And our height again is just r vec, because the distance from r prime to r prime prime is so small that it almost maintains the same position vector from the sun all the way to the planet. So we have r vec there, and that is our dA, right? command force is if angular momentum L is giving us what the position vector across the linear momentum. Okay, so result in Roman 1, Roman 2, Roman 3 above show that the ADT is a constant. All right, so this is a very interesting part because again, we're looking at, we're using our dA from before, which is just half V delta T cross arrow vec, right? That's our dA from before. Now, we can get the ADT here because again, remember I want to show that the ADT is a constant. So we can get the ADT here to be what? Half V cross R, because this velocity goes down, so we have the ADT, so we have not V, half V cross R. Now, but our angular momentum is actually position vector cross linear momentum. So we can simplify that into our position vector cross mass, that cross velocity, because that's linear momentum, right? Mass times velocity. So you realize that our arrow cross V is basically our angular momentum L divided by the mass. Now, there's something very important that we're about to establish, that angular momentum divided by mass is a constant. Now, let's show you how that works. Now, you have to take note that if I differentiate the angular momentum with respect to time, that gives me the torque that is acting on the particle at that particular point. So the best way I explain this to students is really that think of force in normal mechanics. The force of normal mechanics is defined as the time rate of change of momentum, right? Now, in rotational dynamics, angular torque is rather defined as the time rate of change of angular momentum. So torque is really to rotational dynamics as force is to normal mechanics, right? So while force is time rate of change of momentum, torque is time rate of change of angular momentum. Now, but take note that angular momentum is zero on this particular planet, right? And so if angular momentum is zero, if torque is zero, then the derivative of this particular function with respect to time that gives you zero implies that that function is a constant function, right? So wherever you differentiate something and the result of that derivative is zero, that means that that thing initially was what? A constant. So it means that our angular momentum here must be a constant since the derivative is zero. So L must be a constant. Now that is very important because then it now permits you to say, now watch this. This is our dAdt here, which is half V cross R. Now, our V cross R there is L over M, right? This is our L over M here. So this L over M, and then we'll have V cross R. So we have V half L over M there. L is a constant, M is a constant. That means that the dAdt is a constant. So, right there, that's the proof. So the proof is our dAdt is a constant. Now we can go ahead and then show for Roman 5 that using the constant expression of the dAdt above, express V1 over V2 in terms of R1 and R2. So to solve this, I need you to realize that this relationship we've just established here simply says the dAdt is a constant, which again, I need you to notice that this is Kepler's second law of planetary motion, right? That the radius vector that links the planet to the sun sweeps out equal areas in equal time intervals, which tells you that the dAdt is a constant. Now, but if the dAdt is a constant, that means that what our angular momentum here is also a constant. Of course, we already established that that's a constant. But then I need you to see that our angular momentum, which is arrow cross P, right? We can write that as R1 M V1 at perihelion. That's when you're closest to the sun. And then that's simply going to be R2 M V2 at the aphelion, which is when you're farthest away from the sun. So at every other point here, this relationship would always hold true because the angular momentum, remember that is constant. So the fact that we have the conservation of angular momentum, as Planck described elliptical paths about the sun, that's an extrinsic interpretation of Kepler's second law, really. So we have this established, so M can go off, and then we have R1 V1 equals R2 V2, which means that V1 over V2 is R2 over R1. And so that's the relationship that we need, and that's what we have demonstrated. And that's it, people. I hope you enjoyed it. I hope you liked the video. Please subscribe, turn on the notification bell, share our content, and see you soon. Keep loving science.